So hello everyone, Deep Learning with Python, the 10th chapter today. And today we will see the time series. So let's start with the contents of the chapter. First of all, we will see some examples of machine learning tasks that involve time series data. And we will try to understand what recurrent neural networks are and how they work. Then we will try to apply some RNNs on a specific task of temperature forecasting example. And then we will see some advanced RNN usages patterns. So let me also start the video so that you can see me and move on. First of all, what is time series? What are some time series tasks? Some examples. When we're talking about time series, we are talking about data that are obtained via measurements at regular intervals. Some examples of such data are, for example, the daily price of a stock at the stock market, or it could be the hourly electricity consumption for a specific city. It could be the weekly sales of a store. So unlike previous kind of data, like the image data that we saw or tabular data, the specific kind of data involves the understanding of two things. First of all, the dynamics of a system. So if something changes, one of the features changes now, how will this change other features maybe in the future? And also that there are some periodic cycles, usually in this kind of measurements. So how it trends over time. For example, there can be yearly cycles, there can be monthly cycles or weekly or daily cycles in many data like this. So we have to understand this kind of dynamics and this time of periodicity in order to get the insights and solve this kind of tasks. Now, the most common task regarding time series is forecasting. So the idea that we try to predict what will be the next entity at a specific series. For example, the next temperature or the next price when we have stock market prices. Now let's see some other tasks apart from forecasting. One could be, for example, classification of a time series. This would involve, for example, the bot versus human based on the visitor. So if a visitor at a website is a bot or a human based on the time series of the activity. So this would be a classification problem. Detection problem would be, for example, the hot word detection that we have in many devices nowadays, like the OK Google or Hey Alexa. So these keywords, these hot words, we try to detect them in a specific time series, audio time series in this case. Another thing would be, for example, anomaly detection. So usually unusual activity on a corporate network, for example, or let's say that we have a production line and we want to see if there is some problem or some issue, or there is going to be some problem in the near future. So this kind of anomaly detection tasks usually are done with unsupervised learning. So this time in this chapter, we will see a forecasting problem, but it's good to mention that there are other kind of problems also in time series. So regarding forecasting, we mentioned some problems, some tasks, for example, the electricity consumption, and this would help to know what demand to anticipate in the future, or the revenue a few months in advance so that we can plan the budget, for example, for a company, or the weather so that we can plan our schedule. So all these tasks of forecasting are everyday life tasks. Now, let's start with the usual way. We will solve a problem and then we will explain how we solved it. So in this case, we will solve the temperature forecasting problem. And the target in this one would be to predict what will be the temperature one day in the future, so 24 hours in the future. So what we are going to use for this specific problem will be time series of hourly measurements of 14 quantities, such as the atmospheric pressure or the humidity or the wind direction and other data like this. But this time we will use time series data. So we will have the measurements taken in specific time intervals. So this data, these measurements were recorded over the recent past by a set of sensors at the roof of a building of the Max Planck Institute building of biochemistry in Germany. The data that we are going to use today cover the years from 2009 to 2016, and these data are recorded every 10 minutes. So we are not going to use this 10 minutes interval, we are going to use hourly interval, and we will see how we can do this. Now, what are we going to try? So we will start with some that we have already seen, and then we will show the new stuff. So first of all, densely connected networks. We have already seen this in all the previous tasks. We will try this here to see what would be the baseline. Then we will move to convolution networks, so convolution layers 1D convolution layers. And then we will introduce the new ones, the recurrent neural networks, and we will see how they work and if they get any better results or not. First of all, regarding the data, so it's the Jena weather dataset. I have already downloaded the data in the Jupyter notebooks. You can find how to download and save the data and process them. So I will just load the data here. I will read the file. I will split the lines, and for each line, I will take first of all the header, where we have the 14 features, the 14 columns, and then we have the this kind of data, which are the lines, and we will read these lines. And here we see what are the categories. So first of all, we have the date and the time. So this is the timestamp. Then we have the pressure, the temperature, etc. So these are the 14 different features that we are going to use. Now, let's parse the data to see what we can do. First of all, the first column is the data, so the daytime. We are going to remove this since we are not going to use this as feature. We are going to use this only in order to know which sample to include in the specific, which step to include in this specific sample. Then we will create one numpy array per column, and we will separate the temperature column because this will also be the target. So the target, I repeat it, is to predict the temperature 24 hours in the future. So we will have one numpy array for the input data, which includes the temperature, and one separate only for the temperature. Now let's see how we will do this. First of all, the temperature will be zeros. We initialize it with zeros, and how many lines we have, that many zeros. And then the raw data will be, again, how many lines we have. And the width will be how many elements we have at the header minus 1, because again, we will remove the date, the timestamp. And then for each line of these lines, we will take the values, we will make them to float. Again, we remove here the timestamp. And for the temperature, we keep the value 1 because it's the second one. The first one was the pressure, the second was the temperature. And for the raw data, we take all of them. So this will be for the raw data, this will be the input data in particular, and this one will be the target, more or less. Okay, so it's reading the file. And we are done. Now let's plot the temperature data to see more or less what it looks like. So here you can see what that first of all, we have lots of data points, more than 400,000. And you can also see that there is this periodicity. So it goes up, it goes down, and more probably this is the year, winter, summer, etc. So you could say that this is more or less highly predictable because you know that if you are around here, it's here. If you are around here, it's here. So why we need something, how difficult would it be, for example, to predict it? Now, if we zoom in and we take 10 random days of this, and you will see that it's not that clear what is the periodicity. So here you can see that if you are, for example, at this point, you don't know what will happen around this area, if it will be here or here. also why this is here. So the idea is that there is some periodicity, usually there is, but it doesn't mean that this will hold if you change the scale. So what we can notice is that, first of all, there is, as I mentioned before, the periodicity. Usually it's daily or yearly, like in the temperature. And also, if we have human-generated data, then it could be also weekly. For example, the different behavior in the weekends in comparison to the weekdays. Some example of this periodicity, as we mentioned, of course, here is the weather. It could be the parking occupancy at the mall. It could be the traffic at the website. It will be the sales at the store, a grocery store, or something like this. Now, let's see how we can compute the number of samples we will use and make also the splits. So first of all, we will have 50% of the total data to be for training, then 25% to be for validation, and the last 25% for testing. Now, one thing that is important here in comparison to the previous examples is that we will not shuffle the data before. We should have the test data to be more recent, so more towards the future than the training data. And this is why we will take the first 50% for training. Otherwise, if we mix them, then we might try to end up to predict the future given the past given the future, and not as we should predict the future given the past. So this is very important. We have mentioned in the past, so pay attention to this one. We started with the training, the next batch will be the validation, and the last time samples will be for testing. Now here we will just take the number of samples and we will keep the indices, so nothing important here. We see that we have some 200,000 training data, 100,000 for validation, and 100,000 for testing. Now let's prepare the data. First of all, okay, we have some, okay, here it is. So again, the task, given the data covering the previous 5 days and sampled once per hour, so not once per 10 minutes, can we predict what will be the temperature 24 hours in the past? So we have the 5 days and then we predict 1 day afterwards. Now, regarding the data and the pre-processing, of course, the network needs numbers, and the good thing is that we already have the numbers, so we don't need some vectorization process as we will see for the text in the next chapter. There is though a scale problem, and we have already seen this. So we have some values that are in 1,000 and some values between 0 and 10, some values between 0 and 1. So we need normalization, of course. And the usual way to apply the normalization is to take the mean and the standard deviation. So subtract the mean divided by the standard deviation. One important thing is that in order to compute the mean and the standard deviation, we do it only on the training data. So from all the data, we take only the first that many, the training ones, and we calculate the mean over the first axis, which means that this mean will be 14 values, one average price value per feature for all the 14 features. And the same thing goes for the standard deviation. So we compute these two, and then we will use these two to normalize the data. Now, in order to feed the data to the model, we will construct a dataset object. And so what we want is to create an object that will yield every time a batch of data for the past 5 days. And also we want the target to be the temperature 20 hours in the future. So now we will see how exactly we will formulate this. We don't need to keep all these samples, all these data points in memory. Of course, we keep the raw data in the memory, but we don't need to keep all the redundant information in memory. So we will generate them on the fly. And this is what we will use, the time series data from array, which is very useful for this kind of cases. Let's see how this works. So here is a dummy example of how this method actually works. So we import Keras, we construct some dummy data, so from 0 to 9, And then what we want here is to have this object that will be the iterator, the generator. Now, let's say that we want triplets of data, so 0, 1, 2, 1, 2, 3, 3, 4, 5, etc. So in this case, we will have this kind of sequence. We will start from the beginning up to 3 before the end. And let's say that we want to predict the third one. So in this case, we will take from the third one up. So this will be the data and this will be the targets. And we can also define what will be the sequence length. So how many data we want? We want 1, 2, 3, we want 1, 2, 3, 4. So how many data points will be, how many steps will be in one sample? So let's see what this will look like, and then we can see some variations. So this specific one gives for data 3 numbers that are all of them, so we don't leave anything out. And the target is the third one. Now we can always change this. For example, we can make this 2, and in this case, it will include 2 consecutive numbers, so 0, 1, and predict 2 in the future, the second in the future, so 3 here. Or we can change this and predict what we want. Let's say we want this 4 and predict 4, etc. So here we predict 3, 4 in the future. So this is the idea how you can play and change how many data points and how much in the future you want to predict. So let's keep it untouched and move on. And now we will see how we will initialize the actual data sets that we are going to use. First of all, I mentioned that we are going to sample hourly data, not per 10 minutes interval, which means that we will define the sample rates to be 6, which means every 6 times 10 minutes. So another thing is the sequence length, which we want 5 days in the data. So 5 days times 24 hours, since we will already have hourly based on this, is 128, this number, the sequence length. And the delay, since we want 1 day in the future, we have this sampling rate times the sequence length plus, this is for 1 day, so 24 minus 1. And here is just the batch size. So the idea is here is that we define the same exact thing for all of them. So train, validation, and test will be the same, with one exception, the start and the end index. So again, for the train data, we start from 0 up to this number. For validation, from where we left the train up to this, and for the test, we start from this until the end. All the other elements are the same. So let's see the other elements. First of all, for the input data, again, we want all 14 data, but with specific delay, so 24 hours delay. So we have raw data and the specific delay. Now for the targets, we want the temperature, but with the delay, with 24 hours in the future. And this is why we write this one. Now the sampling rate is how many we will leave outside. So in this case, we will leave 5 out of 6 in order to get the hourly time steps. And the sequence length will be what we defined before. So for 5 days, we want to sample them internally, only the specific that are from 0 to number of training samples, batch size, just the batch size, and that would be all. So this again is the same exact here and here. So let's run this one and move on. So let's see more or less what will be the output of one of these datasets. So the shapes will be 256, the batch size, the first. Then for the inputs, we will have 120, and this 120 will be for the 5 days. And for each hourly time step, we have 14 features. And for the target, we have just 1 temperature per sample. Again, this sample contains this many time steps, but it's 1 sample. So for each sample, for each 5-day data, we have only 1 number, and 256 because of the batch. Now, I mentioned before that it's good to have a baseline, to start with a baseline, just to know whether what we achieve with any model, any algorithm that we train, if it's better or worse. And the this baseline is usually some very dummy algorithm that runs super fast that we can think of in 1 minute or so. So this is important because, as I mentioned before, sometimes it's quite difficult to beat it. And in these cases, it's always better to know where we can stand without any training. For example, if we have an unbalanced data set with two classes, A and B, and we want to use accuracy to predict class A or class B, and because it's unbalanced, let's say it's 90% and 10%, then a very simple baseline is to always output the 90%, so let's say class A. And if we always output class A in this example, we will have accuracy 90%. So whatever we try to achieve should be more than that. If we achieve 88%, then we can just output always A and have the correct one. So what would be a good baseline here? So for the temperature prediction problem that we have, what will be the baseline is to return always the last known temperature. So what was today at 7 p.m., output this temperature and see how far it is from the 1 day later. Very simple, and let's see how we can calculate it so that we know where we start. So the idea is that okay, we will want to take the average, so we zero these numbers, and for each data point in the data set, we have the samples and the targets, and then we have the prediction. So again, the prediction will be the last temperature. So for the whole batch, we want the last time step of the batch, and we want the temperature. So index 1 is for the temperature. And because these data are already normalized, we want to unnormalize them. So we multiply with the standard deviation of the temperature, and we add the mean, the average of the temperature. So this will be the predictions of the dummy algorithm. And then we just take the difference with the targets and the absolute, we will use mean absolute error as a metric. And then we just take the sum of it, and we just take also the number of patches. So in the end, we will end up with a validation mean absolute error of 2.44 degrees, Celsius degrees. And for the test set, 2.62. So remember this number because this is our baseline. We want something that is better, which means lower than this number, because it's the absolute error. Let's try again. It's better to start with something simple and then move on to something more complex, because then you will know if it makes sense or not. So we will start with a dense layer, just a densely connected network with, we have the inputs. Again, the inputs will be how many time steps we have and how many features we have, which is this number. So we flatten them. We have for the whole 5 days, all the hourly data, 14 numbers per time step. We flatten all of them. And then we pass them through a dense layer here with 16 outputs, ReLU. And then we have the one output, which will be the temperature. And since it's the temperature, we don't need any kind of activation here. And let's run it. So I have already trained it. And let's see the mean absolute error. And here you can see that the mean absolute error for this is actually worse than it would be for the baseline, which is strange. I mean, you would expect that the model would be, actually the model is able to find it because the value that we selected, the last known value 24 hours before, is in the data. So it could just say 0 everything and wait 1 for the last value. And this would be actually better than the 2.66. But it didn't. And the thing regarding this is that no matter if, so it doesn't, the solution, our solution might be in the search space of the model in this case, but doesn't mean that the model will find it by using the backpropagation algorithm. So let's see, first of all, let's plot the data. So nothing new here. The important thing is that we will try, again, the fact that the solution technically exists in the hypothesis space doesn't mean that the model will find it. Now let's see if we can get something better instead of this. So let's try the 1D convolution model. So the same way we have the 2D convolution models for 2D data, we can have 1D convolution networks. And this layer will be applied on the features. So let's see how we can implement this. The idea here is that we will not flatten it, so we will take each sequence length separately. So here we have all the hourly for 5 days times how many features we have, and this will be the input space, the input shape. And then we apply this conv1d. We will use, first we will start with a size of 24, and this 24 means that it will see 24 hourly data, so 1 day data at each step. We will not use any, we will take all of them, we will not skip anything, so strides will be 0 in this one in this case. And we will output, let's say, 8 different kernels, 8 different feature maps. Then we will apply a max pool, be careful here, 1D, not 2D as before, with 2, so that we halve it, halve the size of this sequence. So it will be for 2 hours instead of per hour, more or less. And then we apply the same. So this time we will take again for the whole day, which means that we will have to take for 12 hourly or whatever this kind of data are. Then we halve it again, then 6, then we halve it again. And in the end, we take the average, so one number out of all of this, and we apply a dense layer, and then this will be again the output, one output from the last dense layer. So the convolution 1D is more or less analogous to the 2D as I mentioned before, and it's great to fit any sequence of data that follows the translation invariance assumption, exactly like in the images that we don't care if, for example, a table is at the bottom left angle corner or at the bottom right corner. It doesn't matter. No matter where the object is, we want to try to detect it. The same way for 1D, we don't care where in the time series in the sample is the specific pattern. We want to detect it. Now, okay, let's continue. First of all, let's run this one and see what will be the results. So remember, for the baseline, we had 2.62, and here it's even worse than the dense layer, the dense model. I mean, you would expect that it would be better because it has 1D, it can have the whole information. We don't make it just one big string of number. We don't flatten it. So it has some structure. It can follow the structure. Now, the problem with this is most probably that the data from the morning, from a morning follows different properties than the data from an evening or from middle of the night, which means that the patterns that it tries to detect are not consistent, are not translation invariant. And this was the assumption. So the assumption in order to use 1D convolution or 2D or whatever the convolution is that there is translation invariance in the data. But here there is no this thing, because again, the data, the patterns in the morning and in the evening and in the night, they are not the same. You cannot just translate and expect the same thing. So this is worse. Now let's see if we can actually achieve something better than, again, the baseline. The baseline was very, very simple. And we already explained why this would be worse. So they don't quite respect the translation invariance assumption. And the order in our data matters a lot. So the recent past is also more important than 5 days ago. But the convolution layer doesn't know about this. It just takes all the days and it treats all the days, the 5th day and the 1st day, like it's the same. So we cannot leverage from this knowledge that we have. We cannot pass it to this specific layer. But there are some kind of layers that can hold this kind of information, that knows how to keep in memory this kind of information. Let's see an example of them. So simple LSTM-based model. again, first we will run it and then we will explain it. So same input here, nothing new. The new thing is this one. So LSTM 16 on inputs. This layer, the LSTM, when it will be applied on each sample, again, the sample is for 5 days, all the data, this will output 16 numbers, and this will be the embedding of these 5 days. Some kind of encoding all the information for the 5 days of 14 features in 16 numbers. And then we will take these 16 numbers, again, they don't need any flattening, it's just 16 numbers, and we will pass them directly to the dense layer, and then we will output 1 as a temperature. So remember, what this LSTM does is that it takes whatever we give it, and it outputs, in this case, 16, an encoding of 16 numbers. As usual, I have already trained it because it takes some time. And now, 2.57, which is actually the first time that we have something better than the baseline. So kudos, deep learning could actually help in this one. And this is because of the LSTM. Now, let's see how this thing works and why it actually achieves better results than the baseline. First of all, let's try to understand what a recurrent neural network is. As I mentioned before, both the densely connected and the convolution 1D, they suffer from the problem that they don't have memory, which means that they don't know how to treat differently the first day, the second, the third, and the fourth, etc. Each input shown to them is processed independently. So we have the data, we just flatten them or treat them as separate data, and then we expect the model to find the correct patterns from this thing, which, as we saw, it doesn't really work, and these kind of models are called feed forward. So we feed the data, they flatten or they do whatever, and they pass through the whole network, and we take the output. Now, there is another, so the kind of layers that we are going to see now are quite different. So what we want is to process the information incrementally. And we want also to maintain an internal state and model and update it every time. So take the data, somehow remember the information we need to remember, then take the next time step, then the next time step, then the next one, and keep updating the internal model of these, of what we try to describe with this task. So in the RNNs, we have these things here. First of all, the data point is not processed as a single step, but it's processed sequentially. The network internally loops over the sequence of the elements, and it keeps updates the current state, the internal state of the RNN, for example, and feeds it together with the next input to the sequence. So what we have is that we have the input, this processes the input and produces some output. So the feed forward will stop there and it will feed to the next layer. But here what we have is that this takes only one time step, it processes it, it produces the output, and then it uses the output as input together with whatever internal state there is to process the next time step. Now let's see in more detail how would this work. And we will see it with plain NumPy code. So let's say we have 100 time steps and we have 32 features. And what we want is to output 64 for all these 100 times 32 data. And we want only 64 numbers. So we construct the inputs and we construct all of this, also this state T. So this will be the time state, one state per time step. We initialize it to zeros, and here we have how many, the number of the output, so 64 in this case. And what we will do is that we will keep updating this state. We also create the weights, so the parameters that we will need to learn. And here it's more or less the same as we had in the densely connected. So we have the W, which will be output features time input features, U, which will be again the same, and the bias, which will be just one number per feature. We create a list of the successive outputs, and then for each input, in the input, so for each 32 numbers of the specific time step of the 100 time steps, we take and we do this 100 times. So first of all, we compute the output. Again, the output is more or less same as the densely connected. We have a dot product between the whatever input we have in W plus the bias, but in this case, we also have this term here. So this term is another matrix, another weight, U, and that we multiply with the internal state, the state at step T. And we apply an activation, so in this case, tan 8. So we take this output and we append it to the successive outputs, and then we replace the state to be whatever is the current output. So this will be used in the next iteration. And then in the end, we just stack them and make them one big NumPy array. Now, this would be what is the implementation in NumPy. Now, let's see how we can use this thing. So, a recurrent layer in Keras. First of all, an RNN layer that can process any length, a sequence of any length. In the previous case, we saw that we had in the NumPy array, it didn't matter if we had 100 steps or 50 steps, so how many time steps there are in the sample. Same way, if we define the input to be in the first dimension, the batch dimension to be known, then not the batch, this is the time steps of each sample of the batch. So if we define the time step dimension to be known, it means that we can process any kind of any length as input. And this is good because in some cases we need to deal with different, in this case we don't have, because we know we take 5 days every time. But in other kind of data, we might not have 5 days or this specific number. Of course, if we know it, it's better to define it so that we can activate some, unlock some performance optimization. Number of features. So the way we call any layer like this is that we just define the input, which will be something like 2D plus 3 third dimension for the batch, and we define also what will be the output. So in this case, let's say 16 numbers. Now, what we saw before is that the model in the previous case with the dense layer afterwards is that the model takes all the time steps and outputs this specific number, for example, 16 in the previous example. But there are cases where we want to return these 16 numbers, but for all the time steps in the sample. In this case, we can return the full sequence of successive outputs and not just the last one, the one that corresponds to the last time step. So there are these two modes, either return only the output of the last input at the sequence of the time steps, or return all the encodings, all the 16 numbers, for example, one per for each time step. And this is important. We will see that if we have sequentiative, for example, 2 LSTM layers, one after the other, then we need to return all the outputs of all the time steps to the next one. We will see here, for example, that in this case, we don't want to return the sequences. We just want to return these 16 numbers, and this is why we have non-16. But if we turn this to true, it will work. Yeah. So here we have 16 numbers, 1 per step, and this is why we have 120 times 16. So remember this one because we are going to use in the future. And this is the same for all the recurrent layers of Keras. They work with exact same thing. So you have to define this thing if you want to return for all of them or not. And this has to do with what the next layer expects. So the simple any RNN expects a rank 3 tensor, which is batch size, number of time steps and features. But a dense layer, for example, expects 2D, for example, batch size and number of features. So depending on what kind of layer you have afterwards, you turn this to true or to false. No. So let's continue. Yeah, and here is with true, as I mentioned before, that you take this number. So let's turn this, yeah, false, not right. Okay, so let's continue. Let's see what we can do to achieve better results. So in order to increase the representational power of a network, one can stack many RNNs one on top of the other. And here is an example of how this would work. So we take the inputs, we pass them through an RNN layer, and we turn this to true in order to pass it through another one. And if we want yet another one, we pass it through, we turn this to true also. And this is the way we stack them. We just turn this to true. It's quite simple. So one thing regarding the simple RNN, simple RNN is the function, the function that I showed before. So we have the two matrices and the biases, and we activate it with tanh. This is not actually very good. It just exists in Keras for this kind of examples. But it suffers from the vanishing gradient problem, which is similar to what we have if we stack convolution layers and we don't use any method from the ones that we learned from, for example, the residual connections. Now, the solution for this is either LSTM or GRU layers, and these don't suffer from the same problem as the simple RNN. So they more or less use a similar technique as the residual connections, but in this case we have the carrier. So we have an extra line of information that carries the information across the time steps. So let's see how this works. Now what I'm going to show now, you don't really have to remember or even understand. This is not needed in order to use these networks, but it's good to see at least once. So this is the simple RNN. Again, the idea is that we have the input. We have the input. We start from zeros here, the current state. We produce the output. This will be the output t-1. And then we use this output as the state for the next step. We take the new input and we have the current state. And this is more or less what we saw before. We apply activation on this. So we have W on the input T, and then the U dot product with state T, and we add the biases. So this is exactly what I saw before, this thing. And then we take the output, etc. So this is the simple RNN. Now, what we would do, the same way we use the residual connection, is to add this C, this carry track. So how this works? Instead of feeding only the state of the previous step and the input, we also have this CT. So nothing new here apart from this part. So we add one more term, the VO dot product with this CT. And in order to compute the next carry, we apply this. So we have the output again to be a dot product of this plus dot product of this plus the new term here. Okay, so this part is a new term. And then in order to calculate the new carry, the new CT, the CT plus 1, we take this thing, and this thing is just the dot product of the state with UI plus the dot product of the input with this thing. And here we have the dot product of state with UF. So we just implement this. And in the end, we take the first term times the second term and the third times the fourth, and we add them. And this is what we have actually here. So this would be the LSTM. Now, you could say that when we multiply this CT with the FT, this is a way that we force the network to deliberately forget whatever information is irrelevant. Or you can say that the IT and the KT provide some information about the present and they update the carry track in this track here. But this is just an interpretation that you could give, it's just as something that we found out that it works and we use it. So again, you don't need to understand how exactly this is computed because it's calculated internally, and it's not your job. So just keep in mind that the LSTM cell is meant to allow the past information to be reinjected in a later time. And this helps with the vanishing gradient problem. Now, advanced use of the recurrent neural networks. So what we are going to see now in the next 15 minutes is, first of all, how we can apply dropout, because it's quite different than usually. How we can stack recurrent layers. We saw a dummy example, but we will see it on the actual data now. And also, what are these bidirectional recurrent layers? Now, let's start with the dropout. Dropout is implemented in a different manner in the LSTM, so it is helpful, but we don't just add a dropout layer between LSTM. So the idea is that in order to use a dropout within the LSTM layer, you should use this argument here, so recurrent dropout, and you define whatever number you want. So this is a proper way, but of course in the output, so after you have these 32 numbers as output, you can of course apply dropout on these numbers before you feed them to the dense layer. But internally you have to define this argument to use dropout. So it's not something complicated, you just add this and let's see the results. So this is exactly what we had before, but with this difference. And now the LSTM with the dropouts, let's see, 2.54, which is actually, what did I do? Did I find something? Yeah. So, which is actually better. So without dropout, we were at 0.57. With dropout, it's 0.54. And it could actually, in other cases, become even better. So this is an improvement of around 6 or 7% over the non-learning baseline. So we are good. Let's see what else we can do. One thing, when we plot this, we see that we don't have the overfitting, at least for the next, for the first 20 epochs. It's here, and then it starts to overfit. So again, we have a quite good improvement, and let's move to what else we can do apart from the dropout. One thing we can actually do is to stack many, well, many will be difficult, it takes a long time to train, at least 2, maybe 3 recurrent layers. So the idea is that we are going to use GRU, we are not going to use LSTM, but you can do the same exact thing using LSTM as we did before. And be careful, first of all, here you can see that we have these two, the dropout and the dense is exactly the same. 2 things. One is that the first one, we want to return the sequences. Again, we want rank 3 tensor for this one so that we can feed to the next GRU. The output of this, we want this to be false, which is by default. Second thing is that, again, when we want to use dropout, we use it like this, recurrent dropout, and we define the number. So apart from this, everything else is exactly the same. And let's see what will be the evaluation on test using the stack. We expect it to be better because now we have 2 of them instead of just 1 of them. But you have to run it to know if it works better or not. So we will see, for example, in the future that there are some surprises. You could expect something to work better, but it doesn't. And this one indeed works better. We have 2.44. And this is the best mean absolute error that we have until now. And you see that it's really better than this or even this one. So if you stop, we can see that it increases the representational power of the model, stacking these recurrent layers. And again, you can use the same thing using by applying LSTM. You don't need to use GRU as we did here. So again, big improvement. And if you stack more, you can see usually that it gets better. But again, it takes too long to train. Now, the last thing we are going to see regarding the RNNs is the bidirectional RNN. So what is this? What is the idea behind these bidirectional ones? This is a variant of the common RNN where instead of having one that takes the time steps in the correct order, we actually have two of them, and we feed. So we have two of the same thing, the same regular RNNs that we have already seen, but in this case we feed to one of them the time steps of the sample in this order, and to the other one with the reversed order. And this could cut some patterns that may be overlooked when we use only the unidirectional RNN. So it's quite simple. We pass them through the same data, reverse and regular, through two different RNNs, and then we merge. We can merge with addition, with concatenation, with whatever we want. Now, let's see how we can implement a bidirectional. So the idea is that, so before we had something like this. Now we have this, but we feed it inside a bidirectional layer. So whatever we want to define, we feed it in the bidirectional and we apply the inputs on this bidirectional. This is the only difference you have to make in order to change the unidirectional to bidirectional layer. Then we have the same exact thing here. So let's see how this will perform. And 2.59. So 2.59 is actually worse than the single one, the unidirectional one. Which is strange. You would expect that this has more information because you feed it both ways, so it should be at least the same, if not better, right? Now, this doesn't perform better than the plain LSTM, and one of the reasons could be that the recent past matters in this specific kind of data more than the distant past. So when we have the unidirectional, the last data that the model has access to is the last day, right? So you don't have, I mean, you have at the beginning the 5th day, then the 4th, up to the last, I mean, from the end. And then you have the last day, and this is the strongest, and the one that influences more the temperature that will be 24 hours later. But when you have the other way around, then the last data that the model, the last time steps that it sees is from 6 days before, not from 1 day before. And the predicted capacity of the whole model must now come from only the correct one, the from past to the future one, which means that we actually feed noise, more or less. We don't feed more information, we feed the same or even less information to the whole network when we use bidirectional on this kind of data. So bidirectional are very good, but probably for other kind of data. For example, in language, as we will see in the next chapter, they are very good because in language, it doesn't matter if you read it this way or that way, there is no time in this. In this kind of data, it turns out that it doesn't work always. Now, what we can do to go even further. So these are some of the things that you can do in order to improve the performance based on what we have seen. So again, the best one that we had is a stack of 2 GRUs using the what we used a dropout in both of them, and then a dropout before the output. One thing would be to adjust the number of units for each recurrent layer. So you can experiment. I think we use 32. You can see, okay, if I use 64, it gets better or worse or whatever. You can also experiment with the dropout. We use, I think, 25. You can increase to 40 or 50. You can adjust the learning rate. So this is important. The model might be just fine, but other things like the learning rate or the optimizer itself could be not the best for this task. You can also try using a stack of dense layers as the regressor on top of the recurrent layer. So you don't have to use only one dense layer after the recurrent ones. You can have one or two before and then have the output. Or you can improve the input to the model. So you can try to use a longer or shorter sequences, or try different sample rate we used per hour. Maybe something different works better. Or you can actually start doing applying some feature engineering. Maybe some of the data that you have from these 14 data are not useful. And again, if you feed noise to something that is not useful, data that don't have information, useful information within, it might get worse instead of course, better, but even the same. Now, let's summarize and close this part and continue with the questions. First of all, when approaching a new problem, it's always good, as we saw in this example, to establish a common sense baseline with the same metric that we are going to use for the training algorithms. And as we saw again in this example, it's not always easy to beat the baseline. And this is exactly why we need to have some kind of baseline to know if we achieve something or not. Secondly, try to use simple models before you try to use some more complicated or more expensive ones. If you had this running, all the trainings, you would see that the dense was very, very fast. The recurrent, especially the stack of two, it takes a long time. I mean, even if you run on a new GPU, it takes time. So don't spend time, especially if you want to use this for inference and something that is not on GPU, it will be costly. So start from very simple, and we will see in the next chapter, sometimes simple things work better. Now, when you have data where the ordering matters, for example, the time series data, then recurrent networks, as we saw before, are a great fit. They are made for this kind of cases. So they outperform the flattened ones, like the dense or the temporal data, all this kind of time series data. When you see time series, go for recurrent, most probably you will have a quite decent result. Dropout, again, when you want to apply dropout on one of these RNN layers, like LSTM or GRU, you have to define this argument, the recurrent dropout. And stacked RNNs provide more representational power to the model than the simple RNN layer, but again, takes way more time to train. So treat them with caution. So don't just stack many of them and leave it running for, yeah, I mean, you could, but yeah, you have to pay attention how many you will stack. So that would be all. Thank you very much. And